Good afternoon, everyone, and welcome to our webinar. Thank you for joining us this afternoon. My name is Jomana Abdulrazik. I'm studying for a master's degree in petroleum engineering at University of Houston, and I will be your moderator this afternoon. Today, we're pleased to welcome Dr. Yasser Elshayeb, a very special guest from Egypt. Dr. Yasser Elshayeb got his bachelor's degree in mining engineering from Cairo University in 1990 and had his PhD from Nancy School of Mines in France on the contribution of fuzzy logic to geotechnical risk assessment of some ancient tombs at the Valley of the Kings in Egypt. He had a major role in setting up the Euro-Mediterranean policies and dialogues on higher education, research, innovation, and culture. Dr. Yasser currently works as a professor of engineering at the American University in Cairo. And today he will continue to share with us his expert opinion on quantitative data analysis. Please feel free to send your questions in the chat box and we will answer as many questions as possible. With that, I ask that you give your full attention to Dr. Yasser Elshayeb and help me in welcoming him. Please welcome Dr. Yasser Elshayeb. Hi, Dr. Yasser. Thank you for joining us
So,
again today to pick up where we left off in quantitative data analysis.
thank you very much. Thank you, Jomana, for the introduction. Good afternoon, or good morning. Sometimes in some places in this world, good morning. In other places, good afternoon. Today, we're going to continue a little bit with the meat of the quantitative data analysis. We will go a little bit deeper into the course. The last time was about introduction. Why do we need data analysis? Why do we use it? Why humanity actually is using data, is using quantitative analysis? A lot of those talks. Today we're going to focus a little bit on some of the practical aspects, and I'll show you the plan in a minute. One point that I wanted to highlight is that data analysis or analytics, sometimes we call it, you may have heard about the term big data or data mining or data analytics or business analytics. All of those terms are very much related to each other. It comes with time, it comes with the development of science, and actually they are in every science of today. People working in supermarkets use data analytics. People use in reservoir estimation and petroleum engineering, they use data analytics. I have personally applied some of the tools of data analysis in data mining as well for water injection prediction in some of the oil fields in the Gulf of Mexico. A lot of other people will use it for marketing purposes, for civil engineering, for mechanical engineering. Data analysis is everywhere. Wherever there is data, there is a type of analysis that we need to do afterwards. So maybe I'm not speaking about data analysis from a petroleum engineering or an earth science point of view per se, but it's the same concept that could be applied everywhere, of course, in any type of science, as I said before. Well, let's go on. As maybe announced before, maybe you've seen this slide before. It was announced that this is the course plan. This is the plan that we will be doing throughout the 6 sessions that we will spend together. Today is the second one, and the first section we should have tackled what's data analysis, randomness, and maybe some of the tools. Today we will speak about data and data banks. We speak about statistics. Give you some reminder about statistics. I know it's a difficult subject. Not all of us likes it. It's a bit difficult. Maybe it's the way that we were taught that was difficult. Maybe we didn't understand why we have to take this course about statistics. But maybe today we will see some of the usages. Today also I'll be going through I'll going to the data, what we call the data matrix, and I'll show you some of the data matrix. And I'll end up this session today by here, typology of data analysis techniques and the data preparation. I'll do it afterwards. I'm sharing with you actually my desktop because I'll be navigating. This is the PowerPoint presentation that contains everything. but then I'll be navigating also. I'll be using Excel at some point of time. I'll be using Safari as a web browsing at some point of time. So I'll be moving from one software to another. So in order not to lose attention, in order not to share screen every time that I move from one software to another, I'll be sharing my desktop so to show you everything that I have. This is the plan for the session of today. Statistics and probability. I'll go very rapidly over it and show you some examples. Then I'll focus on the data matrix, the preparation of the data, which takes something like 60 to 70% of the time of data analysis. We spend it actually on data preparation. And I'll show you why we do that, why we need to do that. Then we'll move on to the geometry of the data matrix and the topology and cycle of data analysis. Statistics, we've all had some notions of statistics, even in schools. I think maybe in grade 9, grade 10, you should have had some notions of those statistics, like the mean. You had some grades at school, and then you were maybe interested in the mean, or maybe your parents or maybe your teacher have shown you the average score for a particular course or for a particular exam at school. Sometimes in grade, I think 10 or grade 11, we start going a little bit deeper, and we speak about not only the average, but we also speak about the median, the mean, the mode, how to draw data, how to draw histogram, and things like that. I'll just go rapidly into this by saying that usually in life, in order to create data, what we called before in statistics sampling, we had two ways to create a set of data and then to study it afterwards. One way is to take a sample of that data, like you have the population of a country X. Let's take the country Egypt. You have 100 million people living in this country, and you want to study something on that population, like the age of that population. So in order to do that, you will not, of course, be able to go on the street and ask everyone, what's your weight, what's your height, what's your age, what's your weight, what's your height, what's your age. In order to do that, we usually rely on sampling. So we take a sample of that population, and that constitutes our data, and we do some statistics on that sample. And we usually, we will try to imagine or to inference, and this is a statistical term that we use, to say that whatever I will measure on that sample is actually a representative of the whole population. It works perfectly in these days. We're living in a world today where everything is done by elections, is done by polls, is done by going to offices and give your opinion as a population, as part of the population. And usually before the real elections, you hear about polls, you hear about expectations. So they will tell you that nominee X or nominee Y will be having 60%. His index of popularity has increased by 40%, by 20%, by 10%. We expect in the next elections that Mr. X will gain and Mr. Y will lose. Of course, when we do that, those institutions that does that, they don't go and ask everyone. If you take the example of the United States of America now we have an elections coming in November, and we have two nominees, Mr. Trump and Mr. Joe Biden. And you will, if you open any news channel, you will find that there is like an index that says that if the election will go tomorrow, then Mr. Trump will win by 52% or 53% or 55%. How would we get those numbers? We get those numbers actually on a sample of data. So it's not real data, because we cannot afford actually to ask everyone in the United States whom will he vote for and repeat this same thing, every week. So we take a sample of that population and we ask that sample. Sometimes we call them over the phone, sometimes we ask them to come to offices and give their opinion. And when we do that, we measure the result of the elections on that sample, and we would say, well, as I just said before, if the elections will go tomorrow, then Mr. Trump will win by 52%. And usually, and this is something that we don't actually, as population, we don't pay a lot of attention to it. Usually, when this number is mentioned, there is always an asterisk. There is always a disclaimer saying that this result is based on a sample of data that is of the size of 1,000 people, 2,000 people, 10,000 people. And it has been done on a population that is representative of the population of the United States of America, for example. So this is a way to do statistics on large populations. And it goes for everything. I mean, if you want to draw some of the characteristics of an oil field that's in the Gulf of Mexico, and you want to know the average the average density of the oil that is produced from a single oil field, then you need to go and measure the density of every liter of oil that you will extract from that oil field. And of course, you cannot do that. So what you do is that you take a sample of the production of that oil, and then you you measure the density, and then you say that, okay, well, I would estimate that this 5 liters or 10 liters that I've taken from that oil field are representative of the whole or the whole oil field, and I can give estimates for the density, for example. It goes for everything. It goes for when you go to when you want to know when every one of us will go to a medical lab in order to do a medical check, and the doctor will ask you for a complete blood picture. And this complete blood picture will give the doctor an estimate of the number of red blood cells and white blood cells that you have in your blood. And of course, we will not go and check every every cubic centimeter of blood that is in your body. We take a small sample of your, usually it's 1, 2, 3 cubic centimeters, and we analyze those, and we have the data on those, and then we come back and say, well, this guy has this amount of red blood cells or white blood cells in his body. It goes for everything. I mean, it's a usual practice that we we do. And this is what we call the descriptive statistics. Like, you take a sample and then you describe the whole population, and then you do what we will call inference. Like, whatever I have measured on this data is actually a property of the whole population itself. So this is a way of taking samples. The other way that we use actually to generate data is to do experiments. Like, I throw a rock, a small piece of rock with a certain power. I'll throw it somehow, and then I'll measure the distance that has been that this piece of rock has traveled somewhere. So, and I'll repeat this process for like 20 times, 100 times, 1,000 times, and every time I measure what I've done, I measure also the speed of light. I measure the speed of the speed of wind, and I measure also the temperature, maybe the humidity, maybe whatever I was wearing, maybe whatever my weight, the time of the day, the hour of the day, and so on. And all of this I will put in a table, and I will call this table my data that is about this specific experiment. And this is also another way of getting the data that we have. Now, I'll just move over some statistical concepts. And the first concept is the concept of probability. And it's I mean, it's as easy as that. I mean, probability of an event E or of an event X is the number of times that this event E occurs over divided by the number of possible times. I mean, probability of having, I mean, of throwing a dice and having the number 1 is 1/6, because you have only one side that is 1, and you have 6 sides of that dice, so it can fall. Of course, if it's not manipulated, it can fall on any one of the sides. So the probability is 1/6, and we usually express the probability in terms of percentages. And this usually shows us that usually probability does not or should not exceed 1, should not exceed 100%. So if I say that the probability of obtaining number 1 or number 2 or number 3 is 1/6, that's like 16.666%. So, I mean, it cannot be over 100. There's nothing called probability of 120, for example. Even if in our usual jargon of talking to each other, we use such thing, but mathematically speaking, there is nothing called more than 100. And also, there is nothing, surprisingly, there is nothing called 0% probability. We as scientists, we as, let's say, mathematicians, we use approximative numbers. So when the probability is 0.00001, we say, well, you know, it's like 0, but it's never 0. We know that it's never 0. So if anyone will tell you that the probability of, I mean, we can take anything, the probability that the world will end tomorrow, it's a probability of 0.00001%. Okay, but it's not 0. So no one can say that the probability of the world ending now as we speak is 0%. It's not, because it's not. From a mathematical point of view, of course. I mean, I'm not speaking about any other thing. So this is a very important concept that we need to look into. Now, we have also in probability, I'll not get into the details, we have also always in probability what we call the concept of exclusivity or inclusivity. I mean, you have if you have two independent events that are happening, and those events are completely independent, then with the time, I mean, scientists with time were able to have combinations of probabilities together. Like if you will throw two dices together at the same time, what's the probability of having 1 and 1? So this is a probability of event E1 and event E2. And you will find that usually the probability of event E and 2 is the multiplication of the probabilities of those ones. So if I will say that probability of event 1 of having 1 dice falling on the number 1 is 1/6, that's like 16.6%. And then the probability of having another dice falling at the number 1 is also 16.6%. So the probability of having 1 and 1 will mean that we have to multiply the probability of 16.6% by 16.6%, and then we get the total probability. So this is the general concept that we are that we use. Another concept that we also we use a lot in probability is the OR function, what we call the OR function. So it's the probability of having either 1 or 3, for example, in throwing 2 dices. And here the probability is like an addition. So you have probability of event A or E1, as I see, I put it here on the slide, plus the probability of having event E2 minus the probability of having them at the same time. So you get, I mean, I'm only saying this because we will not be, I will not get you into the details of how we calculate such thing. I'm just giving you the concept. I'm trying to stress on the concept that there is something called like that you need to know, that there is addition of probability, that there is multiplication of probability. There is also 1 minus, which is the complementarity of something. I will not get into the details of probability for the moment. I'll just move on to another concept. This is a concept that I've mentioned actually last time during the presentation, which we call today the center theorem limit, and some people call it the law of large numbers. And this law of large numbers says that, or intitulates that, whenever an experiment is have a very high number, very large number of population or very large number of samples, usually the result is following a normal distribution. And this applies mainly for any natural events, and sometimes it's also applicable for other non-natural events. Let me give you an example. I mean, we, the panelists here, we are 4 people. Myself, Ahmed, Jumana, and Hassan. If we will measure the height of the 4 of us and the age of the 4 of us and put it on a scale, you will find that there are discrepancy. There is, I mean, my age is larger than their age. My height is maybe shorter than Ahmed. Maybe Ahmed is younger. I mean, you will find like four points on a piece of graph. But if we will make the same experiment on the 1,700 people that are registered to this course, I'm sure that their age will be a normal distribution. I'm sure that their weight will be a normal distribution. I'm sure that their height will be a normal distribution. I'm sure that the number of children that they have will be also a normal distribution. I'm sure that the number of cars that they own will be also a normal distribution. And this is, I mean, this has been proven by a lot of mathematicians all around the world. So it's usually fair when you work with a huge number of data or large number of data to assume that the distribution of this data is normal. And I will tell you why this is important, because it might not be important for the moment, but I'll tell you in a minute why this is very much important. But this law is really very important to retain, to always remember that usually when you work with huge number of data, large number of data, the distribution is usually normal. Now I'll show you 3 distributions that we usually use in statistics, and I will try not to go very much into details. The first distribution is called the binomial distribution, and we use this binomial distribution, which in cases where we have only 2 probabilities, pass or fail. Like you're observing you're in a factory, and this factory is producing water bottles or Pepsi Cola can, and you are looking into the defective cans that are coming out of a production line. It could be a car, it could be you're looking into the viscosity of the oil that is being produced from below the ground, and if the viscosity is below a certain threshold, this means that this oil is bad, it's not good. While if the viscosity is above a threshold, then this means that this oil is very good. So, I mean, you have 2 modalities: good, bad, pass, fail, good can, bad can, good boy, bad boy, good output, bad output, and so on. So if you know the probability of success, then using some laws of distribution, which we call here the binomial distribution, you can actually predict how many failure cases you can have in the future. For example, this is in a factory, and the probability, let's say, of success, probability of having a good can is 56%. I mean, we measured, we sampled the production of the production line, and we have found that the probability of having a good can, not a defective one, is 56%. Of course, this is a very low probability. I mean, usually in production lines, we're speaking about 99 and 98% or so. But let's make this hypothesis that there is a probability of success of 0.56 percent, or sorry, 0.56, which is 56%. Now, if you have a production line that is producing 8 cans, what is the probability of having 4 good ones? And this is the usage of a binomial distribution. If you would like to look for the probability of having 4 good ones, the probability is about 0.20, I would say 0.25. So 25% is the probability of having 4 cans. Probability of having 8 cans that are all good is approaching actually 0. It's very low. Probability of having 1 can that is very good is also very low. And as you see, the distribution is going up and then going down. You can use, of course, you can play with this distribution, and you can draw a lot of and you can use it in different ways. Another distribution that we usually use is the Poisson distribution, and it's very similar to the normal distribution. Sorry, to the binomial. On the contrary, that we have usually a large number of data, and the probability of failure is usually approaching 0. So I mean, it's a different distribution. I mean, I will not get intentionally into details into this. I really leave it. I will leave it really up to you to maybe Google binomial distribution and Poisson distribution, and you will find a lot of examples how to use it, how to apply it. And as I said before, I mean, in a binomial distribution, for example, you can use it in probability of failure of a machine that you have in the field, probability of having producing an oil that has a low viscosity or low caliber or low whatever. I mean, probability of producing less than 500 barrels of oil from a certain well. This is the way that this is a way to do it. Poisson distribution as well. You can of course use it, and then comes I don't know where is the maybe it's not in this presentation. Then comes the very famous normal distribution that I've presented in the webinar before. I'll go to Safari here to just show you. I'll type here normal distribution, and here it is. This is a lot of graphs that are speaking about normal distribution. Let's take this one. Let's look into this one. And as I said before, whenever the number of experiments or number of data is very high, usually we can assume that the distribution of the data is following a normal distribution. And the good news is that normal distribution has been studied since many years, and has been analyzed profoundly by many scientists, many mathematicians, many statisticians, and now we think that we know it very well. We know how it's moving. We know how it is behaving. When we say, I mean, when you tell me that I have a phenomena that is following a normal distribution, it clicks something in my mind, because I know that this distribution is so and so and so, is behaving so and so and so. If I will tell you that the age of the people that are attending this course is a normal distribution function, where the mean is, let's say, 25 years and the standard deviation is 3 years, then I can actually reason, and I can actually tell you what is the probability of having someone in this course that is of age 50 or 51 or 60, and how many percentage of the people that we have here in this course have an age that is bounded between, say, 20 years and 40 years. With just 2 pieces of information, that are the mean and the standard deviation, I can tell you a lot of information about this about this population. And this is, of course, has been used many times in many ways. I'll go back to the presentation, and actually I like that when you hear what I'm saying, or when you listen to the webinar, or if I'll call it a lecture or whatever, that that we always have a computer with us, that we always have an internet connection with us, because we can also search for information, as I just did now with the normal distribution. But I will urge you, actually, after this session, to look for the binomial distribution and maybe some of its application, and to look into the Poisson distribution and some of its application, and of course the normal distribution that we will be using a lot. And the good news, again, another good news, is that those distributions and many others are actually available on Excel. So in order to make the calculations, you don't have to go into complex calculations that you do with your calculator. Everything now is embedded actually into Excel, is embedded into Google Sheets. The Google is embedded actually into what's the name of the software of Apple that is, they have pages, they have sheets, yes, Apple Sheets. So, I mean, all of those softwares today, they have, I mean, they are embedding all of those distributions, and you can actually use them. Now, I'll move into this this slide, and probably I'll go to Excel and come back sometime. Now, you have a population that you are taking a sample of it, and then this sample is, I mean, you put it in a kind of a table, and this table you want to analyze, or you draw statistics on it, or you have made some experiments and you're doing some data on it. Or there is a third way that has emerged actually with time, is that you actually grasp or grab information and data from the internet or from the source. Like if you will go to the World Bank website, for example, if you Google now World Bank data or World Bank repository, you will find a huge amount of data about everything and all countries in the world. If you want to know how many barrels of oil has been produced by Egypt in the year 1980, it's in that file. It's in the World Bank database. You can go there, you can extract that information, then you can work with it, and then leave it afterwards. The UNDP is also doing the same thing. There are actually, I mean, if you look, if you type on Google the word data banks or data repository, I think even that Google has a product called data.google.com maybe, or data repository.google.com, something like that, that is about data, because data these days is like everywhere. It's like produced by everyone. Is like you don't even need to measure anything to have such data. But then, what is this data? I can show you, for example, just for illustration. This is here the data of those who have registered for this course. I'm trying to be very to move very fast, because there are the names and the emails, and I don't want to reveal any personal information about anyone. But you have here a table with the time stamp, and then email address, and then name, and then date of birth. Yes, and then country, occupation, university, company, graduation year, specialization, if others, whatever. This is a data that I didn't actually sample. I didn't actually make an experiment. It's the team of Dr. Ahmed Al-Garhi, who have actually designed a form, and every one of you have answered that form. So in a participatory way, we have created this table of data that I will call now the data matrix. So it's not data that I have sampled, it's not data that I've measured, it's a data that I've, in a way, grasped from the internet. And we can work actually with this data, and I'll show you how to how to work with this data. So in data analysis terms, we call this the data matrix, because maybe because we are engineers and we like matrices or mathematics or whatever. But I mean, anyway, we call it the data matrix because it's a matrix. It's a table, and a table for us engineers is I mean, we like the word matrix maybe. And usually, I mean, those are the specific para, specific parameters of that data matrix. So usually a data matrix, it contains a large amount of variables. So it has number of variables. If you're speaking about, for example, if you're speaking about an oil field, then you need to know the depth, you need to know the porosity of the oil, you need to know the porosity of the reservoir, you need to know the amount of expected oil that you can find there. You need to know where is it geographically, latitude and longitude. You need to know how many wells have been dug into that reservoir. I mean, a lot of variables. We call it variable, we call it sometimes parameters. And it also contains a large number of what we call cases or individuals, which is like the number of the oil fields, the names of the people, the identification of the machine that I'm testing. IVs and DVs means independent variables and dependent variables. Usually, when you measure or when you get the data about specific phenomena, you will observe that there are some of the variables that you are measuring is actually dependent on each other. I can tell you, for example, from my knowledge of earth science, that pressure, I mean sigma, the sigma pressure, the pressure that is found in an oil field is proportional to the depth, because the amount of pressure that is I mean enclosed in this in an oil field is really dependent on how far this oil field or how far is this reservoir is below the ground. Is it 1 kilometer below the ground? Is it 2 kilometers below the ground? And usually the pressure of the oil that is included in this reservoir is proportional to the height. So sometimes those variables are dependent to each other, and sometimes they are completely independent to each other, like the height or the depth of the oil field or the reservoir, and the porosity, for example. I mean, I would think that maybe some of you can tell me it is related, it is dependent, but for me, naively, someone who is not that much into specifications and characteristics of oil reservoir, I think that those two variables are completely independent: porosity and the depth of the oil field. So sometimes we observe that in that. Nevertheless, as I said before in the last webinar, we have found that mathematically all variables in the world are correlated to each other with a varying degree. I mean, I've just said now that the porosity and the depth are, to my knowledge, to my logic, are independent. I can find, I mean, I will not be surprised if you will give me the data of 5 or 10 or 20 or 100 oil fields or oil reservoirs that are in the Gulf of Mexico, for example, and I will be able to find that there is a correlation, there is a relationship somehow, mathematical relationship between the depth and the porosity. Although those who are technical people, those who are specialized in that field, will tell you no, it's not related. And this is actually where we need to differentiate between what mathematics says and what specialized in the field would say. I mean, I as a data analyst, I can work. I mean, I actually worked with problems in the oil field, and I worked with problems in the stock market, in the Egyptian stock market. And I've worked with people in the Ministry of Health and Population in Egypt, and I've worked with people in the Ministry of Transport in Egypt. And every time I produce data, I produce correlation for them. Sometimes they come and say, well, you know, it makes sense what you say. And sometimes they say, no, it doesn't really actually make any sense. The variables are correlated, but this does not mean that they are a reason for each other. And this is where the term that I used, that I employed last time, which says that correlation is not causation. Yes, it is correlated to each other, but it doesn't make any sense. It doesn't mean anything. It's just mathematics. It's just numbers that are, it's just a randomness of life. Also, another interesting phenomena that we observe is that all individuals, all cases are similar to each other. If you will take all the characteristics, as we said before, all the weight, the height, the age, the number of cars, the number of houses, the number of children that we have, of everyone that is in this session that we have now. We have 34 people in this session. If you will take all those characteristics, you will find that there is a similarity actually between every one of us. We are very much similar. I'm very much similar to Ahmed, and very much similar to Jumana, and very much similar to Hassan in a certain way. Maybe in a characteristic that is called sex, male or female. I'm not similar to Jumana, for example, but maybe in age, yes, maybe in weight, yes, maybe in something else, yes. So we have observed this in large databases, that all individuals are really similar to each other, and we actually can build on that. Now, we usually divide variables into quantitative variables and qualitative variables. Variables that are the parameters that we observe, and quantitative variables are like continuous. They are measured. I mean, like porosity. Porosity could be anything. There is maybe a minimum porosity and maximum porosity, but it could be anything in between. The height of an individual could be anything between maybe 1 meter and 2 meters or 3 meters, whatever. Could be anything in between. Could be 1.8111. It could be 1.62. It would be 1.95. It could be anything. Then there is what we call quantitative discrete, which is like counts. So how many children do you have? 2. It cannot be 2.5. Cannot be 3.1. It has to be 2, 1, 3, 4. How many barrels of oil are you producing from an oil field? 500. Cannot be 500.2. Has to be 500, 600, or 501, 502. Depends on the scale. Then we have the ordinal quantitative, which is like first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. This could be thought of as, for example, when we speak about geography and the geographical position. So there is the equator, and then there is 1, 2, 3, 4, 5, 6 until 90 degrees, and then 1, 2, 3, 4, 5, 6 until 90 degrees in the south, and they are ordinal. They are, I mean, 1 is preceding 2, is preceding 3, is preceding 4, is preceding 5, and so on. But all of them are quantitative. Then comes qualitative variables, and we use qualitative variables a lot in earth science. For example, in my domain, in mining engineering, we always use the word humidity of a fracture, or even for a fracture, we call the fracture is open, is closed, is hairy, is cracky. Humidity, it's humid, it's damping, it's wet, it's dry, and all of those qualitative variables are important. And there is a huge branch of science in this world that is called how to quantify the qualitative variables. If you have a variable that is male, female, for example, or undergraduate, postgraduate, so that's a qualitative variable. How will you quantify it? Shall we put male 1 and female 2, or be politically correct and say female 1 and male 2, or put 0 and 1, or undergraduate is 1 and postgraduate is 2, or what? I mean, this is a big discussion. This not even the discussion. This is a big science that is called how to quantify the qualitative variables, and there's a lot of theories behind, and there's a lot of things behind. As I said before, all those data are the results of experimental or non-experimental research, and usually the data matrix is presented like this. Usually you have less number of variables than the number of cases. You have a lot of cases, and then you have fewer variables, I would say. It's very rare that you will find that you have a number of variables that is larger than the number of cases. If you look into the world map, for example, you have like 170, maybe I'm mistaken, I think 175 countries in this world that are well defined and known by the United Nations. And then you will measure a certain number of variables on this 170 something countries. Usually you will measure 30, 40, 50 parameters. You have 500 wells that have been dug into the Gulf of Suez. Usually for every well you will measure like 20 variables. 500 wells, 20 variables. So usually the number of variables is less than the number of cases. And I can also show you here. I can come back to the data that we have on you as webinar registration. We have here until column K. So A, B, C, D, E, F, G, H, I, J, K. We have 11 parameters or variables, while we have 1,700 cases. Every one of you is a case, has registered to this course as a case. Again, it's very rare that we find that the number of variables is more than the number of is larger than the number of variables. So now this is the data matrix, and I said that variables, the number of variables is less than the number of, usually is less than the number of cases, and we can see this actually in even in the data that we've collected on you, and it contains a lot of data. It contains variables, continuous, as I said before, continuous, categorical, binary, text, whatever. It contains measurements. It contains grades. Could contain ranges of values. Could contain also proximities, and we will come back to proximities maybe after 2 sessions from now. The measurements of proximities, it's very important. Multiple modalities, like the question that was asked during the registration. Are you a student, undergraduate and employed, or postgraduate and employed? And this is the multiple modalities, and or it can also contain some frequencies. So it contains a lot of data. I mean, there's a lot of things that are joined here in this in this what we call the data matrix, and this data needs to be studied, needs to be analyzed, and this is actually the base of our work. This is why I'm speaking about it today in the second session, because this is the base of our work. As I said before, we can consider the data that I have on you as participants here as my data matrix, and let's try to maybe to play with it, in a way, analyze it and look into how to do it. Time constraint. Beginners would think that it's not important, or will neglect its time. Usually, I mean, if we speak about a data analysis process, so it contains a lot of sub-processes, of course, analyzing the data, looking into the data, analyzing the data, and getting results. I'll speak about this cycle right after. But an essential part of it is the data preparation, because usually the data that we grasp from everywhere or from anywhere is not ready for an analysis. Usually you need to do, it's not usually, it's in every, I mean, all the time that, I mean, every time that I had a data matrix, I had to prepare it, I had to work it out in order, before doing the real analysis. And just to give you an estimation, I mean, people would estimate that it takes between 60 to 80% of the time that you will work on the data for data preparation. It takes so much time. Sometimes you may think that it's not important, but if you will do the analysis, you will realize that sometimes you need even to come back to the data to prepare it in a different way in order to work with it. I'll tell you about the data preparation. Sometimes you need to discretize what we call discretize or transform the continuous values into ranges. Sometimes you need to do that. If you want to draw the depths of the 500 oil fields of the 500 oil wells that you have dug in the Gulf of Suez, if you want to draw them on a timeline, you cannot draw them as points. You need to draw them as ranges. So you will say, I will take the amount of oil that is coming out of every well, which is ranges between 2 barrels and 1,000 barrels per day. You cannot draw this two barrels to 1,000 barrels per day on a timeline. You need to give them into into ranges. So you will say, okay, well, I will count how many barrels, how many wells are producing barrels that are between 0 and 50 per day, 50 and 100, 100 and 150, 150 and 200, and so on and so forth. So you are actually transforming your data from a continuous value to ranges. So this is the same that you will do, for example, for the age. And usually we use age ranges. I mean, we never put in any results exact date. We usually speak about the date range between 0 and 10, which is childhood, 10 and 20, which is adulthood, and then 20 to 30 and 30 to 40 and then 40 to 50 and so on and so forth. Usually we do that, and this is also very important. It's very important for the understanding of the data itself. Then comes coding, which is a way to transform qualitative data into quantitative data. And as I was just saying before, if you have a variable called undergraduate or postgraduate, or a variable called student, undergraduate, student, postgraduate, and employed, then you need to code those values into numbers, because otherwise the computer will not understand you. So you need to code them 1, 2, 3, 10, 20, 30, 10, 15, 20, whatever you choose. But you just need to store that system of coding somewhere and not to lose. Some softwares use 100, 200, 300. Some softwares use 110, 101, 102, 103, 104. Some others use 1, 2, 3, 4, 5, 6, whatever. I mean, it doesn't really matter. It doesn't really make any difference. It's only a matter of the system of coding that you are using. And again, you need to register that system of coding, because it's very important to come back to it afterwards. Then you have what we call the normalization, and I will mention it now. I will show you why is it important afterwards when we speak about
it's 19 hours.
Data clustering. Normalization is very important because it transforms the value of it makes all the numbers very close to each other. It's like when you work on those of you who are petroleum engineers, they will understand what I say now. usually when you have a scale and you have a log scale, and the main reason why you take a log scale for your data in order to draw it is that you need to see that the difference between 1 and 10 similar to the difference between 10 and 100. So it shrinks, it compresses the data in a certain way using a log scale, of course. So normalization is a different way of also the data together and making everything close to each other. I'll come back to it in a practical way afterwards. Then comes missing values, and in every data matrix there are missing values, and you really don't have to worry about it. That you have, you have of course to worry about it. You have to minimize the number of missing values, but be sure that there will be some missing values in your data. And the reasons for missing values are very different. Somebody have forgotten to write this number. The computer have failed down. The sensor that you are putting in the oil field in order to observe the viscosity or porosity had a system failure. So for 1 day or 2 days, you don't have any values. So okay, so you need to know what you will do with it. And I will speak about what to do with the missing values afterwards. Then comes also what we call in statistics outliers, values that are completely outside the normal, the usual range, the expected range, I would say. Example would be the height of people. As I said, let's measure the height of everyone that is in this webinar. You will find that the height is ranging between maybe 160 to 180. Okay, that's fine. But then if you will find someone who has a height of 2 meters 08 or 140, that's an outlier. And usually, or an oil field, you have oil fields that are producing something like 200 barrels per day, and then you will find an oil field that is producing 5,000 barrels per day. Wow, that's an outlier. That's a different thing. And usually outliers are not bad thing. They are actually good thing, very good thing. Because this is where you start asking questions. This is where you start asking why. Why is this oil field is producing 5,000 barrels per day? Let's go and have a look at it. Maybe we will find something more interesting than everything else that we have in this reservoir. So this is really important. Why does this guy have a height of 2 meter 08? What happened to him? What made him be so? That's interesting. Why does this guy have a height of 140? Why? Why is it this way? We need to understand. And this is where you start asking questions and then getting some solutions. I will pass the basic statistics. I want to go to, I'll come back to this slide afterwards, but I want to go here to this data analysis strategy. And this is usually what we do in data analysis. You have a problem, you have a research question, you have a question, a simple question. What is the usual production of oil from an oil field in Gulf of Suez, or in Gulf of Mexico, or in the Arabian or the Persian Gulf? What is the amount of oil that is produced by Saudi Arabia in a given year? Let's go and look into the data. This is what we usually do. This is the cycle that we usually go. So first of all, you need to elaborate on the problem or on the research question. What is this question? Why are you asking this question? What do you want to achieve? Because every question could have different answers and could have different achievements for it. So elaborate on the questions. Then we start collecting the data. We need to collect the data about this specific problem. If the problem is I asked myself this question last time, last Saturday. Who are those people that I will be meeting today? Who are they? So I started asking myself, why do I want to do that? I wanted to do that because I wanted to know those people. I wanted to know their profile. I wanted to know their age. I wanted to know which language shall I speak to them with. I wanted to know which speed of speaking to them should be done. I wanted to know which language should I use for the for the presentation. So this is all part of elaboration. Then comes data collection, and actually I didn't do a lot of data collection. I just asked Dr. Ahmed to send me the registration data, and I had the data in hand. Then comes the data preparation. I had to do some data preparation. And I will show you after I finish this slide, why did I have to do some data preparation? Because I had some problems with this data that I was not able to analyze it with. So I had to do some data preparation. And usually when you finish the data preparation, you do what we call the data exploration. So you explore the data, you try to understand this data. This is what I've done last time when I show you the map, and I show you the bar chart with the ages of the people, and then there was this graph. Maybe we can go to Tableau. Yes, this is the file. Yes, I will log in, allow. Okay, now let's go back to Tableau. Okay. So this is my data exploration. First thing, that how many people do I have? 1,716. Okay, good. When did they register? And then I have this graph. Where they come from? And then I have this graph. Egypt, India, Nigeria. And then I wanted to have it in a more graphical way, so I just draw it on a map. I'm just exploring the data. I'm not doing anything. I'm just exploring the data. What's their date of birth? Wow, some of them have written that their date of birth is 2020. This is a mistake. Definitely, it's a mistake. I mean, I cannot imagine that someone has a date of birth of 2020 and he's attending this course now. Cannot be. What's their profile? What's their specialization? That's the answer. What's their specialization again? So they come from petroleum engineering. This is a way of presenting, and then geology, and then others. What's their other specialties? Some of them mentioned others. What's this others? There's 237 that mentioned others. What's this others? Others is chemical engineering, petroleum geology, and so on and so forth. I'm exploring the data. What's their profile? Students, graduate students. What's their graduation year? And I try to maybe reason a little bit here, but I mean, I'll leave this for the next stage. Just exploring the data. I'll come back to the presentation. So data exploration, then comes afterwards some synthesis and patterns. So I now understand a little bit this data, understand a little bit this population of people that I'm dealing with, and I can do some patterns. I can say that, well, the majority of those people are students. Okay, majority of those students are petroleum engineering students. So the language that I need to use in order to work with them is so and so. And that's why I put here communication and pattern evaluation. That's the reason. If I didn't do that, I wouldn't have known that that most of you are coming from petroleum engineering. I wouldn't have used the examples of petroleum engineering, for example, although maybe they are very basic examples, but maybe I would have used, if I speak to a medical students, or students coming from a medical background, I would have used the COVID-19 as an example. If I would have been speaking to business people, I would have been using maybe examples coming from the stock markets or the financial markets. So it depends. And that's why I mention here communication and pattern evaluation. Sometimes in pattern evaluation, this is maybe more interesting. You do classification or prediction. And I will show you what's this classification. It's this sheet. I'm trying here to classify those people. And I'm trying to see, actually to draw some conclusions on them. Do I have a lot of, the hypothesis that I'm putting here, those who have been graduate, who are not students anymore, are they employed or not employed? So I draw just this graph to see what's the portion of the people that are graduate of 2015, graduate and unemployed, or graduate and employed. So this is also very interesting to see. Now I'll go back to the slide to say that after this classification and prediction, there is also communication, and then sometimes you make a decision. If you're speaking about, again, the number of barrels that are produced in the oil fields in Gulf of Suez, you make a decision that we should actually close all the wells that are producing less than 500 barrels per day, because it's not economical. It's not economic to operate it anymore. It's too much wasted money. Then you start asking another question. What should be, for example, the threshold? Why should we do this? Why should we do that? So all of this is actually very important. And then you go back to the same cycle again. So you ask another question. And when you ask another question, you need to elaborate on it. You need to data collect, and then you need to prepare. And then you go on and on and on and on and on and again in this cycle. I can qualify data analysis as the art of asking questions. You ask questions, you find answers, but usually when you ask a question and you find one answer, you usually ask another 3 or 4 questions. And then you go into an endless loop of asking questions and trying to answer them, asking questions and trying to answer them, and so on and so forth. I'll go back to this slide to tell you that those are the main statistics that we will be using throughout this course. And I will not, I think that they are very easy. They are the mean, the variance, the standard deviation, covariance, so on and so forth. Please go to the internet or go to your books, to textbooks, old or new, or go to the internet and search for those concepts. I need you to search for those concepts, not to know them by heart, but just to understand, just to have a feeling for them. When we say the word mean, what does we mean? What do we mean by that? When we say the variance or the standard deviation, what does it mean? Maybe some of you know. Maybe some of you will tell me the answer right now. But maybe many others, when I usually ask this question, people will say, yeah, I remember that we had something like this in the old ages, but I don't really remember. Please go to the internet and try to refresh your memories about those numbers. Now, the last slide that I will project here is this one, which is the typology of the of data analysis, and we have data analysis is a big family of tools. So people have tried to work on them and have tried to make them like classified into 2 big categories, like dependent method, interdependence methods, and then the slide goes on and on and on and on and on, and for the data that are metric or non-metric and so on. In this course, we will touch on those tools that are in blue or in light blue, or not the ones that are in green, or what I see green. I have colors, but I think it's a green color. So we will not touch on those who are in green. We touch only on those who are in blue. And again, this slide, the main purpose of this slide is to show that data analysis methods are like large number of tools and data, and we are actually inventing a lot of them every day. Today, in this slide, for example, you will not find any mention of neural networks or case-based reasoning or profile analysis, and those are tools that have been invented 10, 15, 20 years ago, and they are now being standard in the market. So just to say that there is a large number of tools that are out there. Maybe you will also look into the internet and try to find other tools than the ones that we will present here. But at some point of time, you need to stop yourself at some limit. So the limit that I put for myself are those who are in blue, Those are in green are, of course, important, are, of course, applicable. And, of course, you can search for them and many others looking into the internet. Now, I'll try to go to the data that we had and try to show you some of the problems. This is the data that we have that we want to, for example, analyze. And the easiest way to do is to take it into Excel. I mean, everyone uses Excel, or maybe I'm exaggerating. I mean, most of us are using Excel. So let's take this data into Excel and try to analyze it, try to look into it, as to explore it. So what I will do is that I'll go here, I'll say Control All, I'll select everything, and then I'll copy it, and then I'll go to Excel. I will open Excel, and I'll just paste it here, so Control V. Okay, I have all my data is being extracted, is being brought to here. And excuse me, I'll just take those very small in order not to breach confidentiality of anyone. So yeah, okay, I have timestamp, I have email, I have name, date of birth, country, occupation, university for employed, company for employed, graduation year, specialization, if so and so. Now, let's try to look into this data a little bit from an Excel point of view. And I will enlarge it a little bit. First observation that I had here is that the timestamp is the date and the time where people have registered. Okay. And apparently it's done in a way that is month, day, year, and then the time. But does Excel understand that this is a date and a time, or he understands that this is only a text? And the easiest way to do that is just to do this function, equals that plus 1. And it returns value. If Excel returns value, it means that this data that is in here is not actually understandable by Excel. He didn't understand this. He didn't understand what's written here. For him, for Excel, this is just a text. And if I would like to draw this graph here that I'm drawing with the dates and the times that everyone have registered to, I will not be able to do that. And why I will not be able to do that? Because this is only a text. I cannot use it. So I need to transform this information here from the text to be a number, to be a date. Well, somebody will tell me that maybe I'll have to click here and to specify that it's a long date or a short date, but it doesn't work. As well, here, date of birth. It's 3/27/2000. For Excel, this is text. And for Excel as well, this is a date because it's 2/2/1997. But, let's look at this example, 7/5/89. So the question is 7/5/89, which number is the month? Which number is the day? Is it the 7th of May, 1989, or the 5th of July, 1989? This is actually, it could look as trivial, it could look as very easy to be solved, but it is for me a big problem, because if I would like to see the date of birth of that person, then I would like to understand what are the numbers that are here. And in order to do that, you need to do a lot of, and this is where I come back to the word preparation. You need to do a lot of preparation in order to have the data, all of it standardized, all of it put in the same structure, and so on and so forth. And here you can innovate actually. So you can extract, you can try to extract the month, you can try to extract the date, you can change the parameters of your computer, the system of your computer to understand it. There's a different way to do things. Actually, I tried to do that, to do this, to do this harmonization of all of those data last Friday, and I failed. So what I did is actually I asked Tableau, which is my software that I use for analytics here, to get the data directly from Google Sheets. And this could be a solution. That why do you want to take the data into Excel? Me, myself, Yasser, I like Excel. I love Excel. And I like to work with it. And I know how to manipulate it. And I'm not that much in ease with Google Sheets. Well, it's me. Maybe I'm old-fashioned. But in order to work with it with this data in Tableau, maybe I didn't need to go to Excel in order to work with it. So I had to waste some 1 hour of my time last Saturday before the course in order to prepare this data for the analysis. And of course, if you want to draw, somebody asked me last time about the usage of Excel for analytics, and of course you can do that. But in order to do that, you need to interpret this data. For example, if you want to draw a graph where you have the number of students and the number of graduate and employed, graduate and unemployed, you need to count how many. You need to aggregate those data together. So you need to count how many students, how many graduate and employed, how many graduate and unemployed, and so on and so forth. So it takes a lot of time to do that. You need to aggregate, for example, how many people are coming from Azerbaijan, how many people are coming from Egypt, how many people are coming from Libya, how many people are coming from Iraq. You cannot use the data that is in Excel like this. You need to aggregate, you need to do some preparation, and I go back to the word preparation of this data, and this is why it takes a lot of time. Sometimes the scale that has been used for the data is different from the scale that you have in here. Sometimes you get data that is using the metric system, and while others are using the empirical system. It's really variable, and you need a lot of preparation. Maybe you need to divide the numbers by something, you need to multiply the number by something, and that's why it takes a lot of time to do some data preparation. I'll go back to the presentation because now I'm almost done. I'll be just waiting for your questions, and I'll just wrap up quickly with the presentation, what we've done today. We spoke today a little bit about statistics. Why do we do statistics? The methods of sampling, the methods of gathering data, probability, some notions of probability, the data matrix. Why do we have a data matrix? The data preparation, why is it important? And I didn't speak about the geometry of data matrix. It's not really that important. Maybe you can look it up into this presentation or on the internet. And then finally, typology and the cycle of data analysis. I think by this, it's enough for today. It's been like 1 hour and 23 minutes that we are here. And I think that we need to go on and do something different. But I actually, my mindset is the following. In this course, definitely, I will not be able to tell you about all the information that you need to know. I will not be able to tell you about everything, but I'm giving you the concepts. I'm giving you the usage of it. And I rely actually on you to go to and grab a book on business statistics or statistics for engineers or engineering statistics, or even go to the internet and try to search for those notions and those things and read about them. Because when you will read about them, when you will have some data in hand that you have in Excel, and then you will try to analyze it, this is where you will be able to develop your knowledge of this subject.
Thank you,
stop
Dr.
here, and I'm very much open for any questions, please.
Okay, thank you, Dr. Yasser, for this enlightening session. Now we'll move on to answering some questions. that we have here. Someone says, can the Gulf of Mexico case study be discussed in the future? The honorable speaker mentioned that he personally applied data analysis to water injection in there.
Yes, I have even a publication that has been published on that. I can discuss this, I mean, later in the course, yes, when we speak about neural networks, because we applied neural networks at that time. Well, yes, definitely I can do that. I can show you the case, and I can show you what we were able to achieve using data, only data there.
Okay, well, thank you. Someone says, please recommend a book to study more about quantitative data analysis.
I can give you, I mean, let me show you this. I know that you're seeing my screen now. Are you?
Yes.
Yes, okay. Actually, I don't have a preference for a book, but I'll show you this. In this folder here, I have, I don't know how many, but all of those are books about data analysis and data mining. This is books about data sets, data warehousing, databases, fuzzy logic. I mean, if you will go, statistics itself, if you will go to the internet and search for a book on data analysis, that would be fine. I mean, I cannot recommend a certain book, but any book that has a title that says quantitative data analysis or a multivariate data analysis or even data analysis and data mining, that would be fine. So just search for whatever you like.
Okay. Someone says, did technology facilitate sampling for large populations?
Yes, of course. I mean, technology facilitated a lot because sometimes now we don't even need to pick up I mean, usually in the past, we would have picked up the phone and I mean, I've seen it happening actually, that in large rooms, you have people with the phone book. Remember the days? Maybe you don't remember that. You're too young to remember that. But people like me will remember the days where we had in Cairo, for example, the phone book for Cairo. I mean, everyone in Cairo that has a phone was in a phone book. And we had this book like updated every year. So I've seen people opening that phone book randomly and picking names and calling them over the phone and getting them answers. Now we don't do that. We send maybe SMSs, we send WhatsApp messages, or we get people to go to a certain sites and just register their votes or their opinions, and then we grasp the information from the other side. So of course, technology have eased things massively.
Okay. Someone says, I have problems differentiating between a correlation and similarity. Can the terms correlation and similarity be differentiated, please?
Correlation is a statistical tool to measure the rate of change of one variable with respect to the other. Like you can think of it this way: how many percent will variable A change if variable B change? So this is correlation. So they move with each other. Similarity is like proximity. Is like you put two individuals on we speak about this when we speak about when we go into clustering. But imagine that you have two parameters for a person, like weight and height, and you have two persons, and you will draw x-axis where you have height and y-axis where you have weight, and then you will draw individual one and then individual two. The proximity in the Euclidean proximity, actually, the distance in space between those two individuals is a measure of similarity. So similarity is measured using axes, using parameters, while correlation is a statistical measure between only two variables.
Okay, someone says, can we use the data for reservoir estimation?
Of course. I mean, any reservoir estimation that you have seen in your life is based on data, because no one has gone there to estimate how much oil is in there. What we've done is that we've dug some oil wells into the reservoir, and out of those oil wells, we made the well logging. And out of this well logging, we are estimating the reservoir capacity. So this is all a work of data analysis. No one has been there. No one have seen it before. We are just imagining how it looks like. And all of this is based on data that we have done through, that we have extracted through the oil wells.
Okay, that's about it for the questions today. It was a pleasure having you, Dr. Yasser. Thanks for joining us. This was definitely a very insightful session, and thank you everyone for tuning in with us today. Dr. Yasser, we'd love to have you back. Thanks again.
Thank you so much. And next time, on Saturday, we will be working also with the tool called RStudio. So I would like to ask you all to download it to your computers and have it ready for the next session.